and today we are going to talk about Markov chains, Gibbs sampling for training RBMs, and then contrastive divergence for training RBMs. So it's a longish lecture. I think it's also one of the hardest lectures, just to set the expectation right, and so that you don't doze off. There's going to be a lot of material that we'll cover today, and also a lot of math that we'll do along the way. But I've tried my best to simplify things, and I'm pretty sure that if you just stay awake and attentive, you will get most of the stuff. Okay? Okay. So with that very encouraging note, let's start the lecture. So we'll start with Markov chains. So let us first begin by restating our goals, right? So our goal is that we have a random variable, which is a high-dimensional random variable. And one thing that we are interested in is drawing samples from the joint distribution from which this random variable has come, right? So we call this a joint distribution because it has 1024 random variables, x1 to x1024. I've never seen these guys before. Okay, so we have this joint distribution over these n or 1024 random variables, and we want to draw samples from this joint distribution. And the other thing, or a related thing that we're interested in, is that given an arbitrary function f of x, right, a function of these random variables, we want to compute the expectation of this function under this distribution, right? And that's exactly the two expectations that we're interested in. Those expectations, whatever is inside the expectation, you could think of that as a function of this random variable, right? So given any arbitrary function, we want to compute this expectation. And of course, these goals are related, because if you can draw samples, you can empirically compute the expectation and so on. But just to state them clearly, these are the two goals that we are interested in. And now what you're going to use is Gibbs sampling, which is a class of Metropolis-Hastings algorithm. I don't know why you would care about that, but it's a class of some famous algorithms, and we'll use that to achieve these goals. Okay. So first thing that we'll do is we'll first understand the intuition behind this, and then get into the math behind it. Okay. Okay. So now instead of a single random variable, right, which is x belonging to Rn, suppose we have a chain of random variables. That means I have x1, x2, xk. Each of these xi's belongs to Rn, right? So you could think of this as a friend sending us images on day 1, day 2, day 3, day 4, and so on. So on day 1, he has sent us one image, day 2 another image, and so on. So we're seeing this chain of random variables, right? And the I here corresponds to a time step. It's a discrete time step, day 1, day 2, and so on. It's not a continuous time step. And one example which I gave you was images. The other example could be that I have this n-dimensional vector, which tells me the number of customers in a restaurant on day 1. Then I have the same vector which tells me the number of customers on day 2, and so on, right? So all of these are x's, but they are also associated with times because it's on day 1, day 2, and so on, right? So I have this chain of random variables. So it could either be the number of customers in a restaurant, or the images or wallpapers sent to us on day 1, day 2, and so on. But for this discussion, I'll just stick to the restaurant example, that we have this vector which stores the number of customers in a restaurant, and we have this for multiple days. And just to keep things simple, I'll work with discrete variables. What I mean by that, instead of actually having the counts, I'll just have whether the number of customers was high or low. Okay? Is that fine? Is the setup clear? So we have x, which belongs to some space Rn, not Rn, sorry, 0, 1 raised to n. And then we have several of these on day 1, day 2, day 3, and so on. So that's the setup that we are working with. So we have a chain of random variables. Now on day 1, let x1 take on the value small x1, right? And the small x1 is one of the 2 raised to n possible values, right? So remember that x can take 2 raised to n possible values, right? High, low for each of the n restaurants that we have, right? On day 2, let x2 take on the value small x2, which is again one of the 2 raised to n possible values that it can take on. Now, one way of looking at it is that the state of the random variable has transitioned from x1 to x2 from day 1 to day 2. Right? That's a fair way of saying this. That you're looking at this random variable. The semantics of the random variable remains the same across time steps. It's the number of customers, but just the state has changed from x1, small x1 to small x2. And now on day 3, if I assume that there are x3 customers, then I can say that the state has transitioned from x1 to x2 to x3. And in general, on day n, I can think of it that starting from some small x1 on day 1, the state has transitioned through x2, x3 up to xn, right? Okay? So we are now started talking in terms of states that the random variable can take, and we are transitioning between these states. Now an interesting question to ask would be, what is the most likely value that the state will take on day I given the states from day 1 to day I minus 1, right? Can you think of an interesting application of this? A financially lucrative application of this? Stock market, right? So you know what the stock price has been over the past 100 days, and you would like to know what value it could take on the next day, right? And it's assumed discrete, again, high or low is what you're interested, and not the exact value of the stock, right? Now, more formally, what we are interested in is that we are interested in the random variable xi. Each variable in the chain is a random variable, taking on the value small xi, given the states of all the other random variables that you have seen previously, right? So x1 equal to small x1, x2 equal to small x2, and so on, right? That's the question that we are interested in. Now, suppose the chain exhibits the following Markov property. Okay, so I'm calling this a Markov property because I'm assuming that given the previous state, the current state is independent of all the other states, right? So I only care about what the situation was on day I minus 1. Once I know that, I can determine what the situation is going to be on day I, and I don't care about what happened from day 1 to day I minus 2. This is an assumption again. This is something that we are assuming that the chain exhibits this property, and this ties to all the model assumptions that we have been making so far in the course, right? So we are just making an assumption that this is how our chain behaves, right? So this is exactly what I said. Now, can you draw a graphical model to represent this situation? So the moment I ask you to draw a graphical model, this is the first question that you should think about. What is the first, I mean, such a trivial question that you will not even think about. What are the random variables in your distribution, right? So what are the random variables in your distribution? x1, x2, x3, and so on. The capital Xi's are your random variables. Okay, so that's out of the way. So now let's come to the graph. What are going to be the nodes in the graph? So you'll have one node for every random variable that you have. So these are the nodes in the graph. Now, what are going to be the edges in the graph? I think everyone should be able to answer that, and of course assume the Markov property. What are going to be the edges? The edges indicate what? Dependencies. And what do you know about Bayesian networks? Given the dash, you are independent of the dashes. Given the parents, you are independent of the non-determinants. So you know what you are independent of given what. So now what should be the parent? And I'm asking it very cryptically, but I'm assuming we have done enough of this to be able to answer this. So now, what would be the parent of each node? The previous node. Given the previous node, it is independent of all the other nodes. So you have a very simple Bayesian network where you just have these dependencies between the previous guy to the current guy. Okay, that's very straightforward. Okay. So this property where xi is independent of x1 to I minus 2 given xi minus 1 is called the Markov property, and the resulting chain x1, x2 up to xk is called the Markov chain. Okay, those are just definitions. Further, since we are considering discrete time steps, right? Our time steps are discrete day 1, day 2, and so on. They are not continuous. So this is called a discrete time Markov chain. Moreover, since we are considering only discrete values, each of these random variables is not in Rn, it's in 0, 1 to n, right? So it's a discrete random variable. So this is a discrete time, discrete space Markov chain. Okay, is that fine? Okay. Why are we interested in Markov chains? We don't know yet, right? So we'll get there soon. For now, let us just focus on some more properties of Markov chains, and we'll soon tie it back to our original discussion of approximating the expectation and whatnot. Okay. So let us delve a bit deeper into this and define a few more quantities. So now this, remember that xi can take on 2 raised to n possible values, right? I'll just call 2 raised to n as L so that it simplifies some things for me. So xi can take L values where we all agree that L is equal to 2 raised to n. Okay. Now, how many values do we need to specify the following distribution? How many values do you need to specify this? L square, right? I mean, order L square minus 1. Why L square? For each value of x minus I minus 1, I need to specify the probability of it being a 1 or a 0, right? So this is how it is, right? So I have xi minus 1, which can take on values 1 to L. Now for each of these, I need to define what is the probability of xi minus 2 taking one of these values, right? So I'll have L square total values. Is that fine? Everyone is okay with that? And we can actually represent this by a matrix of size L cross L, and we'll call this as a transition matrix. Why transition matrix? Because it tells us, given a state A at time step I minus 1, what is the probability of transitioning to state B at time step I? Is that fine? So that's why I'll call this a transition matrix. It is a huge matrix. It has L cross L, which is 2 raised to n cross 2 raised to n entries. Is that fine? Okay. Now, and the entry T A comma B in this matrix, although actually I have flattened the matrix here, but you can imagine this is a matrix where you have the xi minus 1 values as the rows and the xi values as the column, and the ijth entry tells you the probability of transitioning from state I at time step I minus 1 to state J at time step I. Everyone gets that definition? Okay. So that's a matrix, and we'll call this a transition matrix. It's a huge matrix. Okay, let's be aware of that. Okay. Now we need to define this transition matrix for all A comma B. That means not the matrix actually. We need to define TAB for all A comma B. That means I need to define this matrix which has all the A comma B values in it for all I. Why am I saying for all I? Say I've defined it for time step 3, right? So it tells me how do I transition from value A at time step 2 to value B at time step 3. Now what does it mean to define it for time step 4? Just repeat what I said. How to transition from A at time step 3 to B at time step 4. Okay. So why do I need to do it for every time step? Why can't I just have one T? Do you get the question? How many of you get the question? Please raise your hands. No, the Markov property tells us that it depends on the previous guy, right? But the Markov property does not tell it that at every point it depends in the same way on the previous guy. And I'll give you a trivial example where it will become clear. Think of restaurants, for example. Monday, Tuesday, Wednesday. Do you see what would happen? For example, transition probabilities may be different for different days, right? So if you take the restaurant, the transition from Friday to Saturday, right, when you're moving into a weekend, may be different as compared to the transition from Saturday to Monday. Do you get that? So from Friday to Saturday, the probability of transitioning from high to high would be high, but on Sunday to Monday, the probability of transitioning from high to high would be low because you would expect fewer customers on a Monday. Does that make sense? So that's why it depends on the time step where you are in the time step. So in general, you need to define it for every step of the chain, right? So you need a transition matrix for every time step. So you need these T1, T2, Tk. As if life was not complicated enough, one T was 2 raised to n cross 2 raised to n. Now I'm asking you to define several such T's, okay? Of course, we'll bring in our savior, which is some assumption. So we'll make an assumption that, and we'll not make an assumption actually. So there are some Markov chains which are time homogeneous, right? So that means that for such Markov chains, the transition matrix remains the same across time steps, right? And this again, you could imagine various scenarios where transitioning from one state to another remains the same every day, right? So if you look at on a given day, and of course under certain assumptions, how many people who had taken a bus today will take a train tomorrow, and vice versa, right? So you would expect over a larger population for these transition probabilities to be more or less stable irrespective of the day. Of course, you can again have the weekend argument there, but still we could have several cases in which we can assume that the Markov chain is time homogeneous, right? And that's a simplified, that just simplifies our life because we just need to care about one T in that case, okay? So that's what this homogeneous Markov chain means, that the probability of transitioning from state A at time step I minus 1 to state B at time step I is the same irrespective of what the value of I is. It's the same on Monday, Tuesday, Wednesday, Thursday, and so on, right? Okay. So this is known as a time homogeneous Markov chain. So we have, so far what have we described? We have described a Markov chain. We observed that it is a discrete time Markov chain. We also observed that it is a discrete time, discrete space Markov chain. And now it's a discrete time, discrete space, time homogeneous Markov chain. Right? That's what we are focusing on, okay? Now suppose the starting distribution at time step 0 is given by mu 0. Now what does this mean? What do I mean by starting distribution at time step 0? What will this be a distribution over? How many values will this be a distribution over? L, 2 raised to n values, right? So it tells us that of all the 2 raised to n configurations which are possible, what's the probability of any of these configurations on day 0 at the starting time step, right? So how many elements does mu have? L, right? So 2 raised to n is what it has, right? So in particular, the 8th entry of this vector tells me that the random variable x0, that means at time step 0, it will take on the value a, right? So this, remember that x itself is a vector, okay? So and there are 2 raised to n such vectors possible. So what mu 0 a tells me is that of all these 2 raised to n possible vectors, what is the probability that x0 will take on the value a, which is one such vector. Is that clear? Okay. Let's be very clear about the dimensions of things here so that there is no confusion. So the dimension of T was L cross L. The dimension of mu is L. Okay. Okay. Fine. Now given mu 0 and transition matrix T, how will you compute mu k? Where mu k is defined as the following, that the 8th entry of mu k tells me the probability that the xk random variable will take on the value a. Do you get the question? What is this mu k denoting? Okay. So let's see. You have x1, x2 up to xk and then maybe even more, right? Now again at xk, this guy can take any of the possible 2 raised to n values, right? So mu k is a distribution over these 2 raised to n values. Is that clear? So I'm asking you at time step k, what is the distribution over these 2 raised to n values? What values can the random variable xk take with certain probabilities, right? And in particular, the 8th entry of mu k again tells me the probability that the random variable xk will take on the value a. Is that clear? Okay. Now what's the dimension of mu k? Everyone. L. Okay. So it's 2 raised to n, and whose a entry tells us the probability that I just defined. Okay. Now let us consider x1. So our first time step was x0. Now I am at x1, and here's what my question was. I'll just repeat the question. Someone has given me mu 0. Someone has given me the transition matrix, and now I'm interested in mu k in general, but in specific I'll start with mu 1. I want to find out what is mu 1, what's the distribution over these 2 raised to n values at time step 1. That's what I'm trying to find out. Okay. So one of the values or one of the entries of mu k is x1 equal to b. So which entry of mu k is this? The bth entry of mu k, right? Just as mu k a was the probability that x1 can take on value, sorry, not mu 1, right? This is the first mu 1. Is that fine? Okay. Now let us consider p of x1 equal to b. I can write it as the following. What have I done here? Introduce the variable and then marginalized over it. This is a fair operation. Okay. Fine. Now let's see. So what does the above sum captures? It actually captures that what is the probability of reaching x1 equal to b irrespective of where I start with at x0 equal to a. Any of the x0s that I start with, I'm just summing over all the possible paths of reaching the value b at time step 1, starting with any value at time step 0. Is that fine? That's what this sum is capturing. Okay, and now of course this joint distribution, how will I factorize it? I can just use the simple chain rule at this point, right? So x0 equal to a, x1 equal to b, x0 equal to a. What is this? Everyone? Mu 0 of a. What is this? Everyone? Everyone? TAB. So that means this is the following quantity, right? So the probability that x1 will take on the value b at time step 1 can be written as a neat function of your starting distribution and your transition matrix. If I know these two, I can compute it, right? Of course, this I've just shown it for time step 1. I need to convince you about this for any arbitrary time step also. Okay, so but at least for time step 1, all of us are convinced, but we do not end there. Let us come up with a more compact way of writing this. So this, what I've done here is told you how to compute one of these probabilities, but how many such probabilities am I interested in? L of these, right? I want to know x1 equal to a, b, c, d up to how many ever entries I have, right? So let us consider a simple case where L is equal to 3 instead of 2 raised to n. So I have 3 possible states and I can transition to the same 3 states at time step 1. And these edges between these states tell you the transition probability. So these are the TABs, and the values that you see under the nodes are what? Mu zeros, right? So these are mu 0, 1, 2, 3. Okay, sorry, mu 0 of state 1, state 2 and state 3. Is that fine? Now let's see what are, and of course again we should always be careful about the dimensions. So this is R cube and this is 3 cross 3. Everyone is fine with that? Okay. Now what does this product actually give us? If I take, this is a vector and a matrix, if I take its product, what will I get? What will I get? Everyone? Are you sure you'll get mu1? Okay, good. So in fact, if you look at it, right, so if I look at the second entry of the resultant vector, first of all of us are sure that this is a vector by a matrix, so the result would be a vector. Now if I look at the second entry of this vector, it's actually a sum of, an element-wise sum of the multiplication of these two vectors, and that's exactly what I had here, right? Mu 0a, where a goes from 1, 2, 3, multiplied by T1b, T2b and T3b, and that's exactly what the second entry of this vector captures, right? All of you get this? How many of you are clear with this? Okay, good. So we can write this compactly as mu1 is equal to mu 0 into t. And I'm sure all of you see where we are headed with this. All of you see that? Okay, but we'll still do it. Let us consider p x2 equal to b. Again, I'll follow the same recipe. I can write it as the following joint distribution. So again, I've introduced the random variable x1 and then marginalized over it. Okay. Again, the same story. It captures how I can reach b starting from any of the values of x2. Again, I'll factorize it using the same chain rule. What is this? u1 of a. What is this? TAB. It should have been T1AB, but we have assumed that T1, T2, T3, everything is T. Okay. So this is again mu1 ATB. Again, I can write the entire thing compactly as mu1 T. Right? What is mu1? Mu naught into T. Okay. So in general, if I ask you mu k, this was actually mu2. In general, if I ask you mu k, what is it going to be? Mu naught into T raised to k. Right? So given the initial distribution and the transition matrix, you can compute the distribution at any given time step, okay, for the given assumptions that it's a discrete time, discrete space and time homogeneous Markov chain. Okay, if it was not time homogeneous, I couldn't have used this, right, because the t's would have been different. Okay, fine. So a distribution at any time step can be computed by finding the appropriate product from this series, mu 0 t1, t square, t cube and so on, and this is all very easy, right? Does anyone see a problem with this? Now I'm assuming that you are given mu naught and t. I just need to give you these two quantities and you are set for life. What's the problem here? What's the problem here? Computation, right? So mu naught is a 2 raised to n dimensional vector, t is a 2n cross 2n matrix. you need to do this expensive computation to get these distributions, right? But later on we'll see that we don't need the full product. We can do something smartly and get by without actually computing this product, but still get the distribution, okay? So that was one set of definitions. Now we'll just do a few more definitions and then eventually get to the point at some point, right? We only have April 26th as the last date, right? So if at a certain time step t, suppose mu t reaches a distribution pi such that pi into t is equal to pi. What does this seemingly profound statement tell us? I hear the word stationary, oh God, honey to my ears, okay. So mu 0, mu 1, mu 2 and so on, right? I was just computing all of these and I can keep computing it and say at mu k, whatever I reached, I'm just calling it by pi. I can call it anything, right? I'm just calling it pi. Now mu k has a certain property that if I multiply it by t, I get mu k back, okay? And here of course instead of mu k, I'm just denoting it by pi. Now if this happens, what is mu k plus 1? It's mu k into t, right? But I already know that's equal to mu k. Is that fine? So now from this time step onwards, the distribution for xk plus 1, xk plus 2, xk plus 3 and so on is going to remain the same. Is that fine? Right? So if this happens, for all the subsequent time steps, you have reached the same distribution. So let's put this in context. We had assumed that t was the same across all the time steps. But the mu's were not the same for all the time steps. They were different. We were computing them as mu 0, mu 1, mu 2 and so on. But now we are saying that if at a certain time step the above condition holds, then from that time step onwards, even the mu's become the same, right? So for all j greater than equal to that time step, your mu is going to be the same, which is pi, and pi is then called the stationary distribution of the Markov chain. Okay, again some definitions. I'm not saying why this would happen or will this happen and so on. Under what conditions this can happen, all that we'll see later. But if this happens, then this is what it would mean, okay? And now you can see that xt, xt plus 1, xt plus 2, all these random variables which are at time step greater than t, actually greater than equal to t, follow the same distribution which is pi. So instead of mu, I'm calling that stationary distribution as pi, okay? And now if I think of samples being drawn, right? So if I'm looking at samples from time step t, so remember that at time step t, the random variable xt can take all of these 2 raised to n possible values, but it can take these values not uniformly, but according to a distribution, which is this mu t is the distribution, which is pi is the distribution, right? Again at time step t plus 1, it can take all of these 2 raised to n values, but according to this distribution pi. So now because all of these time steps have the same distribution, you can think of these samples xt, small xt plus 1, small xt plus 2 and so on, all of them coming from the same distribution which is pi. Is that clear? Does that make sense? How many of you are clear with this? I see a blank, Nikita. You didn't get it? Let's call it T for now. Okay. Yeah. So the key thing to note here is once you reach the stationary distribution, after that, even though it seems that you are having a different random variable at every time step, you are essentially drawing from the same distribution. All these random variables come from the same distribution. All these samples come from the same distribution. Okay, that's a crucial property and we'll return back to it. Okay. So now this is the important takeaway from here. If we run a Markov chain for a large number of time steps such that it reaches its stationary distribution, from that time step onwards, all the samples come from the same distribution. And why do we care about this? What's the spoiler alert here? One of the goals that we had was sample from that intractable distribution. Now whatever you have learned about Markov chains, can you give me the next part of the story, right? Can you tell me where we'll head eventually? We'll try to set up a Markov chain such that its stationary distribution is what is the required distribution? What is the distribution that we wanted to sample from? P of x. So if you can set up a Markov chain such that its stationary distribution is P of x, then if we run the Markov chain for a large number of time steps, we'll know that it will reach the stationary distribution. And once that happens, whatever samples are coming, they are as if they were drawn from this P of x, even though we can actually not compute P of x, right? Of course, there are a lot of ifs here, and we'll look at all of these ifs one by one, but that's the story that we are headed towards, right? And that's why this setup of Markov chains, okay? And what do we mean by running a Markov step for a large number of steps, Markov chain for a large number of time steps? What does it mean? It means that it's starting from time step 0, where you'll draw a sample according to the distribution mu naught. Then at time step 1, you'll draw a sample according to this distribution. At time step 2, you'll draw a sample according to this distribution, and you'll continue doing this. At some point, you will of course reach the stationary distribution, and from there on, if you continue drawing samples, then you will get samples from the stationary distribution pi. So this is what I mean by running the Markov chain for a large number of time steps. Keep drawing samples from the chain at every time step according to the relevant distribution. And what's the relevant distribution? It's either mu naught or mu 1 or mu 2 or mu 3 and so on. I'm ignoring all the computational interactability of mu 1, mu 2 and so on, but we'll try to simplify it as we go along. Right? But that's what I mean by running a Markov chain for a large number of time steps. Okay? Is it always easy to draw these samples? So I have very conveniently written that I'll draw x1 from this distribution. Is it always easy to draw these samples? When in doubt, always say no, right? I just gave you an example that this mu 1 requires a 2n cross 2 raised to n cross 2 raised to n cross 2 raised to n multiplication, right? Mu 1 is mu naught into t. So if I want to compute the distribution mu 1 and then sample from that distribution, I have to do this inefficient matrix multiplication, right? So the answer is not always easy, but we'll have to focus on things which are easy so that we reach our goal. And the reason it's not easy is that mu k, the dimension of mu k is 2 raised to n, which means that we need to compute all these 2 raised to n values and then draw according to that distribution, which is not going to be easy. Now when you have these large number of parameters, what can you do to reduce the number of parameters? You have a distribution which has a large number of parameters, it's a joint distribution, and you want to reduce the number of parameters of the distribution. What will you do? Factorization. Factorization depends on independence assumptions. Did we make any independence assumptions? What are we talking about? Okay, that's not a wrong answer, but bigger picture, what are we talking about? RBMs. Okay, did we make any assumptions there? Independence assumptions? No? We made some assumptions there, right? So that's a missing piece of the story that we'll get to, okay? So we need to somehow be able to compute these joint distributions efficiently, and at some point we'll rely on this factorization that we'll have, okay? Okay, so that ends the first module, and I'll quickly summarize what we have done so far. We have this discrete space, discrete time, time homogeneous Markov chain. We have also defined the starting distribution mu 0, the transition matrix T, and the stationary distribution pi. All this is fine. Why do we care about Markov chains and their properties? This is not clear so far. How does this discussion tie back to our goals? Even this is not clear. So first we'll see an intuitive explanation for why all this is required, right? And then we'll get into a more formal discussion and then actually make it useful, okay?